Welcome back, guys, for our next topic. It's a brand new week. Hopefully, these videos you guys have been watching have been informative and have been able to get you guys the information you need to know. Like I said, I've kind of been reading the comments through on Moodle. I have been not have I've been kind of reading them. I have been reading them, so at least people are watching the video, so that's a help. And I've been answering questions as they pop up here and there. And like I said, hopefully they're doing what you guys need them to. It gives you guys the information. If you do need more information, please feel free to let me know, and I will update the information as needed. I will text you guys, Zoom, whatever we need to do to help make sure you guys get the correct information. So today we're going to continue on with learning about our the next component. So first off, we've done with capacitors and how they respond. Now we're going to deal with inductors. The good thing is with inductors is they follow a lot of the same things as far as capacitors do. The only difference is now they're going to be at a positive 90 degrees to start with versus a negative 90 degrees where the capacitors were. So the nice thing about that too is as we get going, we'll be able to use the exact same patterns and just recognize that we might have positive values instead of negative values when it comes to the angles. So that's going to be one of the big things that is changing. But everything else should be the exact same as far as how to do the math and everything. The only other difference that we have is just how inductors work, the formula for finding inductance and things like that. But like I said as before, we're going to go through all this. My plan is for these sets of videos is we're going to go through the inductor portion. We're going to teach you guys some about magnetism, how it works, what the idea behind it, how, some of the basics about that. We'll get into inductors pretty heavy as far as what they're made of, some of the physical parameters they have, kind of like what we went through with capacitors. We'll go through how capacitors in series and in parallel add. We'll go through those. We're going to talk about Faraday's law, Lenz's law, and then once we get through all those, then we'll start in with some circuits. Like I said, they follow the capacitors pretty close as far as what they do math-wise. And again, the only difference is we're dealing with a positive 90 degrees instead of negative 90 degrees. And then at the end of that, we will get through the series RL circuits in series, RL circuits in parallel. We'll go through series RL circuits, and then the last section we're going to have is we're going to introduce transformers to you guys and let you start working with those. And then next week, I do believe we're working on filters, so applications of RL and RC circuits, and then even getting into RLC circuits, so a combination of a resistor, capacitor, and an inductor. And those ones get to be a lot of fun. All right, so we're going to go ahead and start again. So basically, we got to think of an inductor. An inductor is what? And of course, I'm going to fight with this thing to start with. Maybe. If I can get my pen to work. There we go. All right, so an inductor is simply a coil of wire that interacts with magnetic fields. Okay, so one of the things we need to look at is, so if we have a magnet sitting here, we have a north end and we have a south end. Well, we have these magnetic lines that come out and go around the magnet like this. And we can detect these with a coil of wire connected up to a meter. We can simply just wave them around and we can see that. There was some, I'm sure you guys have seen some of the experiments where we just, you have a coil of wire and you run a magnet through and you see some current generated. Well, that's what's happening. When we deal with generators, things like that, that's what's going on, is we have a set of coils and we have a magnet. And as those spin, the field moves in and out of the coil, which then creates a positive and then a negative voltage, because we have to see the positive and then it sees the negative side as the other end of the magnet comes, or yeah, the other magnet comes through and rotates. So one of the cool things is, like, so how a motor works or a generator works is we have a series of coils, something like this, and then we have a magnet that sits in here with a north and a south pole, and then this thing spins. So the magnet is driven onto a shaft which something then is propelling it. It could be, you know, in the form of a water dam where the water is doing it. So we'd have big chutes coming through here, and on the end of this would be the axle of this guy, and then we'd have great big paddles on each of these parts. So as the water comes rushing down, it turns this guy and starts spinning it around, which in turn causes this to spin, which spins the magnet. And then what happens is we have these magnetic fields. Let me do these in a different color. So we have these magnetic fields that are out and about like this. And so what they do is they go in and out of these coils. So when the northern part, the positive part of our magnet rotates around, we see a big surge of positive voltage, and then it goes away, and then we see the negative part come through. And so now we're starting to see, now we're generating a sine wave based on this rotation. This also works for any kind of generator. It has something that's turning the turbine, whether it be steam in like coal-powered power plants, or even nuclear. It does the same thing. The nuclear rods, they start to break down, and when they break down, they emit energy. The energy gets released out of the nuclear material and goes into a water system and basically heats it up and turns it into steam. The steam then runs through into the turbines, which then spins, and then the water goes out to a cooling system, and then it gets pumped back into the reactor. And so the nuclear reactors, coal-fired reactors, any of those kinds, they all run the same principle, is they're converting the material, energy, nuclear, oil, whatever it may be, into steam. And then the steam is what turns the turbines and gets everything going for to turn the turbines. So now that the turbines are going, we have this generation going. The coils that we have here, those are just inductors, and they are able to pick up these magnetic fields, and they store their energy. They can also create magnetic fields. So you can have it the same ways. You can run a current through one of these coils, build up a magnetic field, and you can actually transfer it over to another coil, which then induces a voltage into that. And that's kind of the idea behind transformers, is we're using this magnetic field so we isolate from ourselves from whatever's generating it to the actual, you know, production of the electricity. And so we build up these magnetic fields, the field collapses, and we can use those in induction. We induce a voltage, hence the name for an inductor, comes from through these coils of wire. It's actually pretty slick how these work. Now, one of the things that we need to know, so we have an inductor. Its symbol is given to us as L. This is the one we use because we already have I that we use for current and a bunch of other things. So inductor comes from L, and it is measured in henries because it was Lord Henry that discovered he discovered that this property, Henry. So now, like we said, just like a capacitor stores its energy. It stores it as a charge, like a physical charge that it stores and has to be dissipated. An inductor, it stores the energy in a magnetic field. So if we were to just take an inductor and plug it up to, let's say, a DC source, when we run this current through, and if we had a meter or something over here, what we'd actually see is if we could see the coil, we could probably see it start to glow a little bit, start to build up some heat. And if we had a meter sitting over here, we could detect, they call it what is it? I can't remember the name of it is, but it measures magnetic poles. Or you could even put a compass. That's the thing too, is you could throw in a little compass right here. So you get your north, south, east, and west. You run a charge through that, and you're going to see your magnet point one direction. And then you disconnect the power. So let's say we throw in a switch to this guy. So we close our switch. We're going to see one of these, the magnet's going to point a direction, the direction of the north of our positive portion. So then when we do, we're going to see it go there, and then what we're going to do is we'll pull the switch out, disconnect it. That magnetic field that we created is actually going to collapse, and it's going to induce a voltage in the other direction, and we can actually see that in our magnet. So it could be pointing, towards true north or whatever it may be, and then when we put on a field next to it, we're going to see it spin and turn out of the way, And then when we disconnect it, we turn the switch off, the field's going to collapse, and then we'll see the magnetic field, and then this magnet will go back to where it's pointing. It's actually pretty cool. But then when we hook it up to an AC source, what we're doing is we're kind of doing the same thing as opening and closing the switch, only we're changing the direction. So we'd see this guy, and he would kind of shift back from where, so we'll just say over here, this is true north, and we'll say this is normal, how it's going to go. So we put the compass right next to it. When we turn this on, it's going to point one direction, and that's it. When the field collapses, it'll go back to pointing true north. So we can control the magnet a little bit, and we can see that through here. When we put in an AC signal, what we're going to see, and if we were to put in our compass again, east and west, what we're going to see is that one phase, it's going to be pointed this direction, and then the next phase, we're going to see it pointed in this direction. And that's just due to the alternating signal and the alternating magnetic field. So we're going to see it go back and forth between these 2 points, whereas this one is going to go from pointing from here when our signal is on. So we have our DC source on to true north with our source off. Okay, so we're going to see it shift a little bit, but this one you're going to fully see it shift directions, point north and then south based on how the wave's coming. And it could be going pretty fast depending on our frequency. So that's kind of basic about inductors, how they work. Some cool experiments you guys can try. So the way this does this is, like we said, the inductor, it stores its energy as a magnetic field. Well, we can measure that. So the amount of work that we store, which we measure in joules, is equal to 1/2 times the inductance times the current squared. And then again, we said, so W is the amount of work in joules and the amount of energy that it stores. L is the inductance, and I is the current. And inductance is measured in henries, and current is measured in amps. And that'll give you the amount of energy that an inductor stores. Some of the physical properties. So the inductance, we can calculate the inductance just like we can with the capacitance. It's equal to the number of, sorry, that's capital N. The number, or N squared times mu A and then L. N is equal to the number of turns in the inductor, so it's a big coil. Think of that Tesla coil that sits above Chris's desk and Brandon's desk in the lab. That Tesla coil, that big red part on there, that's just a coil of wire. So we could actually measure the inductance of that wire and figure it out based on these properties. So N, like I said, capital N is the number of turns. The micro sign is equal to the permeability of the core. Now basically, what is it wrapped on? Is it wrapped around air? Is it wrapped around an iron shaft? Is it wrapped around a magnet like ferrite, things like that? And this is just the value you can get from it. We're not going to be dealing a lot, but I want you guys to understand that this is where these are coming from. A is the surface area. Sorry, not the surface area. The cross-sectional area of a wire. So that means when we're looking at it this way, it's this, we're looking at it flat with the wire kind of going off like this, like that. We're just looking at this surface area right here if we were to cut the wire in half. And then L is the length of the core. L-E-N-G-T-8, length of core. So those are the properties of how we do, of how we're doing these, of how an inductor is made. And you guys could make your own if you wanted. The permeability of the core, it's a value you can find up. There's a chart for it. Like I said, we're not going into these a whole lot, so we don't really care, but this is how this is derived. So you could construct one yourself if you wanted to. Now, one question, like I said, that brings up is the type of core. There's 3 types of cores that we usually use. Now, this is the symbol for an inductor. Looks kind of like a light bulb. If you were to look at a filament, things like that, it's just a curlicue, versus a resistor, which is the triangles. So we have three cores. If the inductor looks just like this with nothing around it, this one is said to have an air core. So it's just a coil of wire, kind of looks like a spring, or it may be wrapped around a paper or a cardboard tube or something like that. So we have air. The next one we have is an iron, and that is this one with two solid lines underneath of it. And the last one has two dashed lines, and this is ferrite, which is a naturally magnetic material found in Earth that we can get. Ferrite magnets, things like that, things you stick on the fridge are usually ferrite in nature. And so it's a naturally magnetic material. And so this way we can tell when we draw it out, and we can give that information as far as what kind of core it is. You'll see these symbols on schematics, especially if they have different kinds of inductors on there. It can help you identify where it is you're looking for, because an air coil is just going to be like a paper or cardboard tube with a wire on it. Sometimes it's just a little package, but if it's wrapped around an iron or a ferrite core, those are big and bulky, and you can usually see where those are at, so it's easier to find things. So if you know what you're looking for, it's a little bit easier. And so these are the three materials we use from. They just have different transmittal properties for the magnetic fields. Air doesn't block anything at all. Iron and ferrite both enhance it in different ways. And again, right now it's not important to understand how those different materials work, just to know that there is different materials. And then, like we said, L is measured in henries. So one of the things we need to talk about here is a couple of the laws in relation to how inductors and how magnetic fields work. So we want to talk about Faraday's law. So Faraday's law can be broken down into two parts. The first one says the amount of voltage induced in a coil is directly proportional to the rate of change of the magnetic field with respect to the coil. So again, the Faraday's law, the first part is the amount of voltage that's induced in a coil is directly proportional to the rate of change of a magnetic field with respect to the coil. So the faster things are moving, the faster the magnetic field is moving through the coil, the faster the voltage spike and the faster the rate of change you're going to get. Okay, so if we come back here to my little crude picture of a generator, the faster this wheel spins, the higher voltages we're going to get. The second part of Faraday's law states the amount of voltage induced in a coil is directly proportional it is directly proportional with the number of turns in a coil. So which basically means the more turns that you have in your inductor, the higher voltage that you're going to get into your inductor. So that's why we're going to see here in a minute, based on the series or parallel properties, that's why we're going to see these changes and how our inductance adds or subtracts. Because remember, like with the capacitors, we can determine, either the distance between the plates or the surface area that each of them has, and that's what controls the capacitance, whether in series and parallel. Same with the inductors. The inductors is based on the rate of change through a magnetic field, which we can't really control that. That's just going to be as we introduce things, we don't want to worry about that. And so this one is going to be directly under our control, is the amount of voltage in a coil is the number of turns that it has. So you can even go through and build your own, and if you want it to get a higher voltage out, you just give it more turns, and it works just as good as trying to change other parameters of it. And sometimes that's almost easier to do. So the other one that we need to talk about is, so we have Faraday's law. We also need to talk about Lenz's law. Now, Lenz was another physicist that came through after Faraday, and he expanded a little bit more onto Faraday's law. He took what he had learned and continued with it a little bit farther. So, like I said, Faraday found out these two parts, that everything is proportional to how fast things are changing, as well as the number of coils in that. So Lenz, he came in and he said, when the current through a coil changes, the polarity of the induced voltage created by this change so the current through a coil, when the current through a coil changes, the polarity of the induced voltage created by the changing magnetic field is such that it always opposes the change in the current that caused it. So again, Lenz's law says when the current through a coil changes, the polarity of that induced voltage created by the changing magnetic field is such that it always opposes the change in the current that caused it. So basically what that's saying is, once we have a field that's established, when it shifts polarity and we start getting the magnetic field gets built up differently, it's going to oppose the voltage that's already there for a second, and then the magnetic field will dissipate enough, and then you'll see this change. And so that's why when we're changing things back and forth, we actually will have a little bit of a delay when we switch directions that we can actually measure. So as soon as it switches directions, it's going to be opposing the new current, and it's for a split second, it's going to hesitate just a little bit before it reaches its full potential. So we'll see these little bit of delays. It's not instantaneous, but we'll be able to see a little bit of delay when we shift polarity. And we can actually use that for timing for circuits, things like that. But just so you guys know that it's not an instantaneous effect when we shift directions on the magnet. There's a little bit of a delay as the current that's already there, the magnetic field is there, is being opposed by the other one until eventually it gets overridden, and then it'll go the other direction. So just kind of keep that in mind. So now that we kind of have a little basic understanding of how inductors work, how the coils work, what we're doing with these, so the idea is now we're going to look at what are the cases that we have. So the cases that we have is when we are combining inductors. So if we start off with our circuit, and all we have is one little inductor. We're going to label him as L1. So the inductance total of the circuit is going to just be L1. That's the only thing that's there. Now, we'll go through our next circuit. Now we have L1, L2, and L3. Now when we look at this, what do you think that we have going on? We're going to come back up here to our physical parameters again. So we want to take a look at this equation here. So what do we have that's increasing when we put things into series? Essentially, what we're doing is we're taking the number of turns and we're increasing it by the amount here. So the number of turns is going up based on this with very little change to anything else. Okay. So when we have this, and for all intents and purposes, the length of these guys of the core isn't going to be adding up in this. The only thing we're changing is just the number of coils that we have. We're using the same wire, we're using the same everything else. So as the number of coils goes up, the inductance is also going to go up, as we can see from our parameters table. N squared, so the more numbers that we have here, it's going to be squared, so it's going to have a larger effect on things. We're going to see this value, going up when this value goes up. So inductance will go up as the number of coils go up. And that's essentially what we're doing in a series circuit. We're adding more coils to our inductors. And we're simplifying it down to one single inductor. So in this case, the inductance total is going to be equal to L1 plus L2 plus L3. And then the next part, when we look at our circuits, we have inductors, and we have 3 of them, and they're all in parallel. In this instance, what we've done is now essentially we have increased the distance of our core. So in this case, our L is going up. So when our little L goes up, the big L for inductance goes down. And remember, that's all based on the physical properties of how we can calculate these guys. So as we increase this, just like we saw with the capacitors, when you increase the denominator, the value gets smaller and smaller. So, and then in this case, we're going to use the reciprocal method. So in this instance, inductance follows all the patterns of resistors. So we've already kind of learned how those work. So in series, the inductance is going to add together, and in parallel, we're going to use the reciprocal method to find it, which also means we can use any of the rules that we want to for solving these guys. If they have 2 inductors that are the same value in parallel, it's going to be half the value of that with 2 of them. If we have 3 inductors that are the same value in parallel, it's going to be a third of that value. And we can use the same formulas. You can also use the product over the sum if there's only 2 inductors, just like resistors. That's the real nice thing about inductors, is we can treat them like this, just like resistors. We don't have to learn about anything new. Capacitors is the only one that's a little different, and that's just because of the physical makeup of those. So now that we have kind of an understanding of how inductance actually works and how to treat it, like I said, we're going to treat it like resistance in this case. We'll add inductors together in series to get a total, and in parallel we'll use the reciprocal method. Now we need to kind of understand, what do inductors do? So again, they're going to oppose a change in AC current. So just like what these guys are doing, so as soon as we throw the switch on our signal, as this thing starts to go to the positive peak on the waveform, it starts building up a magnetic field going in one direction, and then it's going to switch. When we start doing that, these guys are sitting at rest, so they already have an induced voltage. It's just 0. So as soon as we fire up the thing, we're going to see a little bit of a delay, and then when it overcomes the initial charge, so to say, or initial magnetic field on these inductors, then we'll see them charge up and hold on to the magnetic field. And one of the things that you guys learned last semester was when we're dealing with a relay. So there's a pickup current and there's a dropout current. So once these things have established some sort of a magnetic field on them, they don't want to release them. They like to stay where they are. And so that's where Lenz's law comes into play, is they oppose any changes in current. And so what happens is, to get them up to a magnetic field takes a higher voltage to get it going. But once it's there, it hangs on to it, and so then it takes it a while before we back it off, before that magnetic field will finally dissipate. And so that's kind of the application of Lenz's law there. So the opposition to the AC current, the opposition to the change in AC, that's what we get our reactance. So remember, last time we had, so our X of C value, so for capacitors, was 1 over 2 pi times the frequency times the capacitance. Well, when we're talking about inductors, X of L, so the reactance of an inductor to AC current, is equal to 2 pi FL. So just a slight variation on that. And this is also in relation to the more inductance we have, the more reactance we're going to have. We're going to see an opposite effect of these guys. So this is really important when we start getting into next week when we talk about filters, because these two are going to behave very differently. So for example, at higher frequencies, we're going to see this value here for our X of C at high frequencies become really small. Because the F's getting larger and larger, X of C gets really small. But at high frequencies, at the same high frequencies, this guy is almost non-existent. This guy is getting huge. So we have two ends of the spectrum, and then vice versa. At low frequencies, we're going to have a capacitor be a very large value, and we're going to have the inductor be a very small value. So remember those formulas for, especially for next week when we get going. But this is the one we're going to be focusing on primarily this time. So we want to find the reactance of our inductor. So inductive reactance, X of L. That's what we're looking for. And remember our chart. We have our resistance is on the x-axis, which is our real line. Our imaginary line, this is our X of L's. This is our X of C's. So capacitive reactance, inductive reactance. We're going to be looking at a plus 90 degrees, plus J value. And then for the capacitance is a negative J value at negative 90 degrees in relation to the resistors. Okay, so before everything we've been doing has been down here in this lower quadrant. Now when we get into the inductors, it's going to be up here in this upper quadrant. The only other problem is now is inductors like this only exist in a perfect world. So in a perfect world, do only we deal with the inductance of a coil. The problem is because now we're getting into the number of wires or the number of turns that we have of this wire. It's so long. There's lots of things going on there. If we were to actually take apart one of the inductors, you could actually see how long this wire is that is used to create this inductor. So now that we have this really, really long wire, now we have to actually start taking into account the resistance of that wire, because it will play an effect on the circuits. So now with capacitors, we didn't have that. All we had was just a reactance value. So it was just an opposition to AC. That was all it did. It didn't do anything else. But now that we have a capacitor, it has a little bit of winding resistance. So the actual resistance of the wire. So when we see an inductor, this is real world where all there is just inductance. But since we don't live in a perfect world and we actually live in the real world, what we're going to see is it's going to look more like this. And in here, this is inside the package of our inductor. So we're going to see a resistance of the winding, and then we're going to see the impedance or the reactance, inductance of that component. Now physically we can't split these out, but they are there. So just like before, you could take a capacitor and hook it up on ohms and then connect it up, and you're going to have 0 ohms of resistance, or an infinite, or you should see an infinite, not an open, sorry, because there is no connectivity. There shouldn't be. If there is, it's not a capacitor. But with this guy, you should be able to hook it up to your ohm meter, and you can actually measure what the winding resistance of that inductor is. And if you don't account for that, it can throw you off. So for example, at low frequencies, you're going to have a very low inductor or X of L value. So at a low frequency, low F, we're going to get an X of L value that is low. Now, how low? Depends. So let's say we're running at a frequency, we have an inductor in place, and our X of L is now only 15 ohms. Okay? The problem is our winding resistance, when we connect it up, depending on how it is, it could be 25, it could be 50, it could be 200 ohms. So now all of a sudden, we're not just fighting with this 15 ohms, now this becomes a really big issue. If we have 200 ohms of resistance and we only have 15 ohms of reactance, our impedance is going to be the combination of those two. So we have to take that into account. Now granted, when we have a high frequency, our X of L is going to be huge. So in this instance, our X of L could be 15,000 ohms. Okay? And then when we have our winding resistance of say 120 ohms, that 120 not going to make such a big deal anymore, because in series, essentially with with 15,000 ohms, 120 isn't even a drop in the bucket. We won't even see that affected. It'll affect our phase angle a little bit, but probably not enough that we'll actually be able to measure it. The first example, yes, it absolutely will. You will see this phase angle shift all over the place. So that's one of the big differences between inductors and capacitors, is we have to take into account their winding resistance as well. So with that being said, now instead of just looking at it, so we have an X of L value that we're going to calculate for an inductor, and it's going to be some ohms at an angle of positive 90 degrees. But to get the total impedance of this guy, we have to take into account the resistance of the winding plus the J of our XL. So each one of these inductors is going to have a rectangular impedance value just for the inductor itself. So we're adding on a little bit more than what the capacitor was. Because remember, when we have our X of C, let's say it equals, some ohms at negative 90. When we write down its impedance, it was equal to 0 minus J of whatever that value is. But like again, what I said, with the inductors, they're a little bit more of a complicated beast, and so we have to take into account this winding resistance. So RW is winding resistance. And that's just the physical resistance of that coil of wire. And you measure that by hooking it straight up to your DMM. So now, now that we have this impedance total, now we can go through and start calculating for what, for our total values. And like I said, we're going to calculate these the exact same way that we did before. So let's start on some circuits to kind of get these into practice. So the first thing that we have, and I'm going to switch colors. So we're going to start off with a basic RL circuit. We got R1 and we got our L1. R1 is 6.8 kiloohms. Our L1, our inductor, is 24 millihenries, and it has a winding resistance of 71 ohms. So this is how you'll see me write it down, and that's how you'll see it in a lot of the books, is they'll put in this guy just kind of underneath, and as long as it has the ohm symbol, you can oh yeah, that's my winding resistance, so we have to treat it as such. Now in this case, 71 ohms compared to R1, which is 6.8, this isn't going to have a huge effect on our circuit, but to make ourselves more accurate, we need to include it. So in the circuit, we have 19 volts peak and running at a frequency of 97,893 kilohertz. So then the things we're going to want to look for is we want to find what is our X of L1, and that's going to be in kiloohms at an angle. Then we want to find the impedance total of our inductor, because remember we have to include this the resistance of the winding. It's going to be equal to kiloohms at another angle, and it's going to be slightly different. We want to find our I total for the whole circuit. That's going to be in milliamps at an angle. And we want to find the voltage drop across R1 in volts at an angle, and the voltage across inductor 1 in volts at an angle. So those are the parameters we want to find in this equation. So the first thing we're going to start off with is let's find the inductive reactance of L1. So X of L is equal to 2 pi times the frequency times the inductance. So X of L1 is equal to 2 pi times our frequency of 97.893 kilohertz times our inductor value, which is 24 millihenries. The total capacity or total inductive reactance we get is equal to 14.762 kiloohms at an angle of 90 degrees. Now we want to solve for what is our impedance of this inductor, so we can get the total idea and the total resistance, total impedance of this entire circuit. So the impedance of L1, so remember, is going to be the R windings plus the inductive reactance, of this inductor. So we want to turn this guy into rectangular. So we are at 90 degrees exactly, so that means this is going to be a positive J value with no real part. So this guy converts to 0 plus J, because it's positive angle, of 14,762. We know that our winding is just resistance, there's no other component to it, so the impedance for L1 is equal to 71 plus J of 0. That's the total impedance of that resistor, plus 0 plus J 14762. We're going to combine like terms, and we end up with an impedance total of L1 is equal to 71 plus J of 14,762. Now, as we continue and go on, we don't have anything else that we're going to add, so we know that we're going to need this in polar, because now we're going to be multiplying and dividing. We're going to find currents, voltages, things like that. So we need this value in polar so we can be able to do those functions. Okay. So when we convert this guy to polar, remember, we're going to take the real value squared plus the imaginary value squared, and the square root of that at an angle of our arctangent of our plus or minus x value over the real value. Now in this case, it's positive J, so our x value is going to be positive. So we end up with, when we run through this math, we plug all those values in, we end up with the impedance total for our inductor is 14,762 at an angle of 89.724 degrees. Now, this has changed from 90 a little bit because, again, remember, we have a little teeny tiny bit of resistance that we have to account for, but we're not going to see 0.3 degrees on our scope unless we zoom in way far. So we know it's pretty much going to be at 90 degrees, and that's one of the things, but we still have to take into account to make sure that we're as accurate as possible. So now we have our first value, or we have these first two values. We have our X of L1 and we have our impedance total. So right here is our X of L1, and we have our impedance for L1. The next part we want to do is we want to solve for our impedance total, because we have this other 6.8 kilo ohm resistor hanging out in series with it. So the impedance total of this circuit is going to be R1 plus the impedance of L1, so the combined total. And so we can go through this one a couple of ways. We could actually, up here, instead of going through this, solving it down, and getting it in polar, converting it back into rectangular, adding it into the R1 value, we could at this point, right here, that this value that we ended up with, to get to our Z total, we could be R1 plus this impedance, which we already found. So this would be, what do we got? 6.8K. So here we could go with 6.8K plus J of 0 plus the 71 plus J of 14,762. Again, we add like terms, and we get 6871 plus J of 14,762. So we could take that little shortcut right here and end up with this guy, and then we convert that guy into polar, which is going to give us 16,283 at 65,040. Or again, like I said, we can go through here, we can convert this back and forth. So we can, and that's what I did in this sense, is I converted our Or no, this is the way I did it with ours. Because again, I knew we wanted this value, but I knew that we were going to need these guys because we're going to add to it because of the series. So I went back and unconverted this guy back into its rectangular form and added them together because that's what we're going to have to do anyway. Look at your answer, see what's there. Most of the time we're going to need these guys in polar. This is one of the instances where we needed it both in polar and rectangular. So you just kind of have to see, based on your problems individually, what's going to happen and what do I need. Do I need it in rectangular form because I'm going to add and subtract, or do I need it in the polar form because I'm going to multiply and divide? And as we get more practice in this, you guys will start to see this connection really fast and just be able to start putting it into which notation it needs to be in. So in the end, this is our Z total for the entire circuit. We end up with 16,283 ohms at an angle of 65.040 degrees. Now, to continue on solving the rest of the circuit, the I total is going to be equal to the voltage total divided by the impedance total, just like we did before. So we have 19 volts at 0 degrees divided by our Z total, which is 16,283 at 65.04. I total comes out to be I total comes out to be 1.167 milliamps at an angle of negative 65.04 degrees. Now we can carry that through just like we've been doing before. So the VR1 is going to be equal to the I total, which is the current going through it, times R1. So 1.167 milliamps at an angle of negative 65.04 degrees multiplied by 6.8K at 0. Voltage drop across R1 is equal to 7.936 volts at an angle of negative 65.04 degrees. VL1 across the inductor is equal to the I total times the X times the Z of L1. Because before, when we did it with capacitors, we didn't have any resistive part, so we could just treat it as the reactance. But since we do have a real part, we have to do the entire impedance of the inductor to get the correct answer. So we take 1.167 milliamps at an angle of negative 65.04 degrees. That is multiplied by our 14,762 at 89.724 degrees. Voltage across the inductor is 17.227 at an angle of 24.684 degrees. Now, one of the cool things that we can see here is now the voltage drops of our inductors are going to be leading and are happening sooner than the voltages for our resistors, which was just the opposite when we're dealing with capacitors. So we'll see the same shifts, but now the waveform that's in the front that's leading is going to be the inductor versus the resistor. And when we're done, we should be able to measure these values and get these values at these phase angles. And remember to do the phase angle as you find the difference in the time between what is your reference line and what is the actual phase angle of the component you're measuring. So you'll put your lines on your scope for setting time in the vertical position. You'll set when it crosses the x-axis for both those lines, find out that total distance in between. So that's going to give you a delta t. So this is the time between the points. So where they're equal, and I just like using the x-axis because it's a real definite point. And you're going to have your period, which is equal to 1 over your frequency in seconds. This is going to be in seconds. And then you take your 360 degrees is equal to your period, and that's equal to X number of degrees over your delta T. So just kind of as a little side note, remember this is how you calculate it, or how you get it from your measurements that you're seeing on the scope. This is your degree calculation from scope measurements. Scope needs a C. All right, so that is a simple series circuit. So now let's go ahead and do one more before I finish this video. We'll make this one just about an hour long, but at least we'll have covered the series and the basics about inductors. So let's start off on our new circuit. So we have 19 volts peak. We've got 9.724 kilohertz. R1 is equal to 300 ohms. L1 is equal to, our inductor is 11 millihenries, and it has 129 ohms of winding resistance. So again, we want to find our reactance for inductor 1, the impedance for inductor 1, the impedance total. We want to find our current total. We want to find the voltage across the resistor and the voltage across the inductor. So we start out, so X of L1, or X of L in general, is equal to 2 pi times the frequency times the inductance. So the reactance for L1 is 2 pi times 9.724K multiplied by, and that's our frequency, and then by our inductance is 11 millihenries. Our X of L, reactance of inductor 1, is equal to 672.075 at an angle of 90 degrees. Now, we need to find the impedance of this inductor, so we need to convert this guy into rectangular, and because it's at a positive 90 degrees, that makes it a real simple, easy conversion. We can even go through the other method where we take our magnitude of our polar value times the cosine of the angle to give us our real value, or we take the magnitude times the sine of the angle to give us our imaginary value. You can still do that with the same equation. It'll spit out the same values. But just remember that if it's at 90, 0, or negative 90, we can use these quick tricks. So if it's at a positive 90, it means there's no real component, and it's a positive J of the magnitude of this guy. It's not going to change at all. 672.075. So now we find the impedance of our inductor. So we take, remember, we have the winding resistance plus our capacitive inductance. So impedance total is our winding, which is 129 plus J of 0, plus the X of L value, which we just calculated, which was 0 plus J of 672.075. We add like terms together, and the total impedance for inductor 1 becomes 129 plus J 672.075. Now we know if we can look in the answers, and plus also we know we're going to be using it to solve current later, we're going to need this value in polar. So the polar value for inductor 1 is 684.343 at an angle of 79.135. So as you can see, this 129 ohms winding resistance, it actually had quite a huge effect on it, because now we've dropped 10 degrees on our phase shift, which is important for when we're measuring these things to get those right. 10 degrees is a lot. That we can actually measure. So there is our total impedance for our inductor. Now the next step, we need to solve for our Z total. Now again, we're going to have our R1 plus the impedance for inductor 1. And so we can go ahead and go back and look, because we already have this guy right here in rectangular form, and we know what resistor 1 is. So our Z total is going to be equal to our 300 plus J of 0 for the resistor, and the impedance is 129 plus a J of 672.075. Again, we add like terms together. Our Z total ends up as 429 plus J of 672.075. We're going to convert this value to polar, and it ends up being 797.324 ohms at an angle of 57.449 degrees. So now remember also too, one thing we can double check to make sure these values are looking right is as the real value and the X of L value start getting closer and closer, we should start seeing this angle approaching 45 degrees. If they ever were to equal, this would be 45. So it's kind of a little check that we can. And again, if it's closer to on the 90 side, then it's going to be more inductive, so you're going to have more inductive reactance. If it's closer to 0, that means your resistors are bigger, and you're going to see, and it's going to be getting closer and closer to a real value instead of an inductive value. So here is our impedance total for the circuit. Now we're going to solve for I total. We remember it's our voltage total divided by the impedance total of the circuit. So we take 19 volts peak at an angle of 0 degrees. We divide that by our impedance, which is 797.324 at an angle of 57.449. Our total current we have in this circuit is 23.83 milliamps at an angle of negative 57.449. Now that we have our total current, we want to solve for the voltage drops, and the total current is going to be the current for each of the individual components. So voltage across R1 is going to be equal to the total current times the resistor value. So 23.83 milliamps at an angle of negative 57.449 multiplied by 300 at 0. So the voltage of R1 is equal to 7.149 volts at an angle of negative 57.449. And then we're going to look at the voltage drop across L1 equal to our current total times the impedance of L1. So 23.83 milliamps at an angle of negative 57.449. And that's multiplied by 684.343 at an angle of 79.135 degrees, which is what we found earlier. The voltage drop across this guy is equal to 16.308 volts peak at an angle of 22.686 degrees. Now again, remember we started out with 19 volts, and we have 7 volts across the resistor, 16 across the inductor, and if you were to just add those guys together, you're going to get a value higher than what we started with. But you got to also remember that these guys are out of phase, so we have to treat them differently. So with them being out of phase, we could go through, convert these two voltages into its rectangular equivalents, add them together, and we're going to get our 19 volts at 0 degrees again. So even though they may look a little odd, if you're wondering about it, you can always go back through and use your Kirchhoff to double check to make sure you're doing them right. Now in these ones, I'm very confident that these are the right answers. I've double checked them several times. But for you, like I said, you can get into the habit of doing your double checks to solve for those values. You don't have to if you don't want to, but it is an option for you. So anyway, with that being said, that's the end of the series circuits. The next video I'll have up, hopefully here today, or I will get it up tomorrow, but this will at least get you going on the labs and on the homeworks, is the parallel circuits. Again, we're going to do the exact same things we did with our capacitors. We're using inductance values, and we'll solve them the exact same way. So with that being said, enjoy, get some practicing in on these guys, start working through them. And again, please let me know if you have any questions.